要2304哪一个关系？2404，我没有调，那你调还行哦。那再一个，你之前不是吃东西？哦，对对对对，好的，就在你这样，妈妈那这他们两个一起吃，还是跟那个鸡蛋，对不对？哦耶，对对对对。那你们看那个，好奇吗？要的，我的感受。要不要去服从？我们一般会来这啊，一般会来这，我人啊，你们一般会吃，是，可是那个时候3.0也是，哇，可能啊，去年见我是，我来做是，去年他们也是讲了同样的话题，3.0没错，是这样子。那你现在上那个对，是学校的什么？有点写的，一般会就学校的校庆嘛。I mean 那时候他们在读书还是在放假的，就是他们星期日的，一定放在星期日。他们没有读啊，只是帮忙做一般会的东西哦。是学期还是我们读书的？我们啊，我们啊，对，我们是第一个 sem，他们是第一个，他们是第一个 sem 啊，我第二个。是要考试的那一个星期，所以就快9点了。嗯，testing 1 2，wait，testing 1 2。Okay, good morning to everyone. So yesterday we stopped at Abel test and Dirichlet test. So both tests has a similarity that we want to prove that the infinite series of product of term converges. But we have different condition on A, N, and Bn, right? Okay, so anyone remember what's the condition on A, N, and Bn here? For both A, N should be monotone, correct? Then, of course, we need to use monotone convergence theorem here, right? Okay. How about Dirichlet A? Converge to 0. Good. Very good. Okay. How about Bn? For Abel's test, we want the series of Bn converge. For Dirichlet test, we just require the partial sum, okay, the partial sum of Bn to be founded. Okay, so yesterday we discussed that they can't imply each other. Okay, they can't imply each other. But if you go through the proof, it's really similar. You want to bound the term that drop out from the summation bypass. Okay. So I mean, you see, in these two cases, can I swap AN and BN or not? Can I swap it? I can swap, right? Because I just regard AK as BK, BK as AK. I can commute.
commutative. Our multiplication is commutative. If in the case that you know that, for Abel's test, infinite series of AN converges, but BN is monotone and bounded, then you still can apply Abel's test, right? Because product of number is commutative. Okay, does it make sense? Okay, yeah. So you can swap it. Okay, you can swap around. Right? So what I mean is, you can regard this series as BK times AK as well. Okay, so you can swap it because it's commutative. Okay, so in that case, you can consider like sum of AK converges. Okay, A goes to 1 to infinity, and Bn can be monotone and bounded. Okay, so there's no issue on the order. Right, good. So let's look at two examples here. Okay, let's look at two examples. Can you use your calculus 2 knowledge to determine whether these two series converge? Have you learned in calculus 2? Can you use it here? There's a factor of -1 to the n. What's that? Alternating, right? So first thing you can try alternating series test, right? Okay, so alternating series test, what do you need to satisfy to use alternating series test? Non-increasing, okay, non-increasing, and also every term inside converge to 0. Okay, is it true for these two cases or not? Right. Okay, so you can see that 1 over n times what? 1 over n times 1 plus 2, 1 over 2n should be greater than 1 over n plus 1 times 1 plus 2 over n plus 1. Okay, and the bottom, 1 over n should be greater than 1 over n plus 1, correct? And then you look at the limit of 1 over n times 1 over n times 1 plus 2 to the negative n. This one should goes to 0. Is it 0? 0, right? Because what is in the product here is convergent. Okay, so this 1 over n converges to 0, and then this part converges to what? 1, right? 1 plus 0 in particular. So go to 0. And obviously, limit of n to infinity of 1 over n is 0. Okay, so by alternating series tests, they converge. Okay, actually, the second one is very familiar, right? There's a name for the second series, right? What's the name? Alternating harmonic series, right? Correct? Because harmonic series diverges. Okay? Yeah, harmonic series diverges. So, but alternating harmonic series converge. So, alternating harmonic series is converging conditionally. Okay, so this is the first case we see what series converge conditionally. Okay, because the absolute value of this series doesn't converge. Okay, so it doesn't converge absolutely. It converge conditionally. Okay, but so we want to use this Abel's test and Dirichlet test to prove the same thing. Okay, can we use Abel's test or not? Okay, so let's look at the first one. Okay, see if we can use Abel's test or not? Okay, see if we can use Abel's test or not. So Abel's test, we require that sum of Vn converges, and also An is monotone and bounded. Okay. Can we use Abel's test to get the same to check that whether it converge or not? What is Bn? What is An here? Try if can set any one of them as An and Bn.就你呢？今天小房？嗯。Yeah, try think about it. So whether these two cases, can you use Dirichlet test and Abel test or not? Yeah, try and discuss. Yeah. Say again. Uh-huh. Wait, so you are thinking so you think that An is 1, is it? Oh, can can. Oh, no, that's fine, because it's not trivial, at least. Because to show that the sum of Bn converges, you still need some convergent thing here. You still need convergence. Yeah, try think. I let you think for 5 minutes. Try first. See what you can do. For these two cases, see if you can apply Dirichlet test or Abel's test. Okay, for these two cases, try think if you can set any useful An and Bn. Try if you can how to split the term inside the series into two useful product of terms, such that you can use Abel's test or Dirichlet test. Because by alternating series test, we know that it converges. So if it can satisfy the sufficient condition for Abel's test or Dirichlet test or not. If not, why? Okay, if yes, then you should be able to find what is A and B at that point. Right. And try. You want to try now? Okay. So which one you want to try? First part, Abel test. You want to do Abel test on first example, is it? Okay. So what's Bn you want to try? Okay, minus 1 to the n over n, because this is the alternating series, right? We prove that it converges by part 2, correct? And then an is 1 plus or negative n. So this term here is bounded, bounded by what? 1 plus 1 over 2. Okay, we start with 1, so 1 over 2. Okay, for every n, correct? No? Monotone, right? Because when n increases, you add 1 to the 2 to the power of n. Okay, yeah, good. Okay, so we can use Abel's test on this guy. Can we use Dirichlet test on it or not? Dirichlet test. How? An be the minus 1 to the power of n over n and be the 1 plus 2 to the negative. Okay, so let's check. So an surely converge to 0, right? But is it monotone or not? Not right. Because you go up, down, and then up, down, up, down, up, down, up, down. Okay, not quite monotone here. Okay, so maybe you say, oh, throw it away, throw this term. Maybe don't want this. Put it to Bn, no? Can or not? This is the only choice, correct or not? Because otherwise it won't work. So I push it to Bn. No? If I push it to Bn, okay, the problem is the m partial sum of Bn bounded? Is it bounded? Why is it bounded? Why is it bounded? Bounded by what? If you say it's bounded, it should be bounded by some number. Okay. Yeah, that's right. You can try and compute what is B1, B2, B3, and so on to see the pattern. This is the correct way to do it. Okay, you really need to work on the ground and then see it. So, okay, let's try. So what is B1? At least, is it? Okay, B2, right? B3, what's this? 5, 5 over 4. B2, B3, negative 2. 10, number 8. Okay, good. Then B4 is 17. 17 over 16, something like that. Okay. So, hey, this bounded is not bounded terms, it's bounded partial sum. So bounded partial sum means what? You need to consider B1, B1 plus B2, B1 plus B2 plus B3, like that. Okay. Yeah, no. Okay. Is this guy bounded or not? I want to claim it is not bounded. Can I just straight away say? Without this negative 1 to the power, can you see that it is unbounded? If it is without this power, can you see that it is unbounded? Because every time you add a 1 plus extra thing, the sum already contain in 1. Every time you have to add 1. Yeah. Then, yes, correct. That's right. And if I put this negative 1 in, still fail the divergent test. Still fail. Okay. So let me see. Okay. So if I take away this negative 1 power, right? Okay. Can you see that this series diverges? Can you see or not? 1 plus 2 to the minus n. So every time you add is 1 plus half, 1 plus 1 to the 4, 1 plus 1 to the 8. So it get increasing, right? Increasing. And then how to show that it diverges? So you can use like what Larry said just now, divergent test. Because the limit of Bn is not 0, then the series have to diverge. But intuitively, if you look at the sum, it contains 1. So every time you need to add at least 1. Sum of 1 is infinite. Okay, you can use a simple comparison test. Sum of 1 diverges. Okay, then this should diverge as well. You can use simple comparison test as well. And then, so if you use the test for divergence, right, then even if you put this powers in, what's the limit of this guy? It is not 0 also, right? It's not 0. Okay, so what we want to claim here is limit of Bn doesn't exist. Okay, so diverges. Okay, that doesn't exist. Or I just say Bn diverges. Then Bn diverges. Okay or not? Does it make sense? Bn diverges.
I was thinking one.
Yes, cancel, not cancel. That's right. That's true also. That's true also. So the problem here is cancel, not cancel, cancel, not cancel, that whether it converge or not. But we can use divergent, divergent test to see that the series would converge. Because the Bn is not converging to 0. Okay. If it converges to 0, you still cannot deduce, might have a chance to diverge. Harmonic series, converge to 0 every term, 1 over n, 1 over n plus 1. But still diverge, harmonic series. Use the Gauss proof. Euler proof or Gauss proof? I always confuse these two guys. Yeah. Okay. So here Bn diverge. Can you see why Bn diverge here? Because the 1 plus 2 to the minus n diverge. Okay. So if you add in the minus 1, it's just putting every term alternating above and below x-axis y equals 0 line. Does it make sense? Does it make sense? You should okay, maybe plot this guy out. How to plot this guy? You could first plot the part. You can first plot the part 1 plus 2 to the minus n. Okay, so what is this? Is 1 plus 1 half. Okay, and then 1 plus 1/4, and then so on like that. Okay. Okay, but the line it converged to is what? Actually, this line should be y equals to 1 line here. Let's draw the 0 origin here. Correct or not? Okay. Once you put this -1 in, what happens? What happens? Once you put the -1 factor in, the first term becomes what? The first term becomes negative, right? So this term go all the way to the bottom. Okay, second term you still keep it, but the third term go to bottom again. And then the fifth term, so the odd term all go to the negative part. But does it converge or not? No, right? Because one of them converge to 1, the other converge to -1. Okay? Yeah, they don't converge to, it is very far away from 0. At least epsilon equals to 1. Okay? Yeah. Okay. So we can't quite use Dirichlet test for the first example here. Okay. Yeah. Yeah.
Technically, for the Dirichlet test, we only series itself is bounded.
Is it bounded? Is it bounded or not? Oh, okay, correct, sure. I mean, wait, let me think. If it is, if wait, let me think. If it doesn't converge, oh, sure, there's another possibility that the series jump. So oscillate, yes. So whether is it bounded or not? Okay, cool. Right. So is it bounded? Is it yeah, is it bounded or not? Let me think. Can we bound it or not? So what we have now is so let's move this guy down. Okay. What we have now is the infinite series of Bn diverges. Now we can ask whether it is bounded or not. Is it bounded? Is it bounded? So maybe let's look at a few terms here. What happened in the sum? Let's look at a few terms and then see what happened in the sum. So first sum is 3/2, obviously, minus 3/2. And then second is minus 3/2 plus 5/4. This term is what? You computed, Joshua? Negative 1/4. Okay. That's 3. Yeah? Negative 11. Oh, okay. Negative 11. 11/8. Okay. And then did you compute more or not? So, okay. So wait, let me put S1, X2, X3, S4 is negative 5/16. Any more? Okay. Okay, let's see if we can see any pattern or not. Let's see. So how do we compare this number? If we don't make it into same denominator, it's a bit hard to see. So maybe make it into 32. So the first one should be negative 48. Okay, good. And then the second one, negative 8/32. This one is negative 44 over 32. And then negative, this one is 10 over 32. Okay, so what's happening here? So we go from negative 48 to negative 8, and then back to negative 44, and then go up to, not too far, negative 10, and then go to negative 41. Seems like it is bounded. Seems bounded. Okay, seems bounded. I think we can show that it's bounded actually. I feel like bounded below by this S1 and bounded above by X2. Seems like works. Yeah, I think we can try at home, show that I think can be bounded by these two numbers. But what I want to say is, even if you can use Dirichlet test, right, you cannot use the same. You can't use the same AN and BN from Abel's test to satisfy the Dirichlet test property. This is what I want to say from this example. Does it make sense? Okay, if you try to put this minus 1 to the power back to AN, okay, it wouldn't work. Right or not? Okay, because AN is no longer monotone now. So we play around with this monotone and convergence to zero property here. Does it make sense? Okay. So it seems like if I push this minus 1 to the power n away, it seems like I can use Dirichlet test. So let's try at home whether we can show this series is bounded below and above by this two S1, S2. Feel like can. I think can. Okay. But we should write it out. Yes. Scrub.
I think there might be an easy choice of A and B.
Which one? For which?
Yeah, just get negative 1 power n. You will throw the 1 plus negative n to A.
To AN. You mean this one move here, huh? Okay, so let's see. What's this doing here? Okay. Yeah, sure. This one. Okay, because AN, we don't need to care about the series anymore. So we just check whether it is monotone or converge to zero. Okay, if it converge to zero, then good. And minus 1 to the power n is bounded, so you can use this one also. Okay. Yeah. Okay, good. Okay, but the problem here is I want to say that if it is true for Abel case, the choice is true for Abel test, it might not be true for Dirichlet test. Okay, this is what I want to say. Okay, so this is the example of Abel test cannot imply Dirichlet test. So you can see that if I'm gonna use Dirichlet test, then we need to make a different choice of AN and BN. Okay, that works for Abel's test. Okay, does it make sense? Okay, okay, yeah, okay, good. Okay, I think this is quite good. So any problem, any other questions on these two things? Okay. So yeah. Okay, so you can see that something that works for Abel's test, the choice that works for Abel's test might not work for Dirichlet test. Similarly, if you take the Dirichlet test choice, it might not work for Abel's test. Okay, it might not work. Okay. Okay. Anything I want to add here? No. Okay. Okay, so this is the thing I want you to take note that Abel's test doesn't imply Dirichlet test and Dirichlet test doesn't imply Abel's test. Okay. Okay, so you also can try Dirichlet test and Abel test on this alternating series here, right? You also can try it on here. let's continue. So let's make some flow chart here. So what's the overall strategy to check for convergence? Okay. So what's the first thing if I hand you a series? What do you do? What's the first thing you do? The first thing you can do, you can straight away use test for divergence. Okay, you straight away ask whether all the AN converge to 0 or not. Okay. If no, what happens if no? Then the series definitely diverge. Okay, by divergent test. If yes, we can't conclude anything yet, right? We can't conclude anything. Because, for example, the harmonic series is converged to 0, but the infinite sum diverges. Okay, so what can we do next? We can ask whether it converges absolutely or not. Okay, you can ask whether it converges absolutely or not. So how to check this kind of series converge? So there's all sort of series you can check. You can use P series. Okay, if it is a P series, then for what P it converge? Or you can use geometric series. Is it a geometric series or not? Okay. And then you can use simple comparison test. Okay, you can compare it with the series that you know that whether it converge or diverge. And you can use limit comparison test as well. Okay. You can compare each term AN and BN. What is their limit? What's the limit of their ratio? Right. And you can use integral tests. Right. We'll go through integral tests. And so the new thing we add is something called the Cauchy test for series. So this is the same as the Cauchy sequence. Okay, Cauchy sequence. You check whether the n partial sum is Cauchy or not. Obviously, we have this so absolute convergence test you can use, but if you don't know whether it converges, then you can't really use. But okay, I think we remove this one. This one is for the next part. So also ratio test, right? And then root test, and then Abel test, and then Dirichlet test. Okay, so there are a lot of tests you can use here that we have proven before. So if it, okay, you check that, oh, converge. So meaning this AN should be absolutely convergent, right? You check its absolute value, sum of absolute value converges. Then AN should be converging absolutely. So if AN converge absolutely means what? It means that AN converges by the absolute convergent test. Okay. If not, what can we do? If no, what can we do? Okay. If no or cannot decide, what can we do? Okay. What can we do? We can proceed with what? Maybe there's a alternating choice you can use. Okay. Like the alternating harmonic series, you cannot decide. So what you do? You can use alternating series. Okay. If yes, then what? If yes, then who converge? Then AN converge. Okay. Because we are checking AN. Okay. If not, if not, how? If no, again, what to do? no more test to use already. So you just check their partial sum. So this is the flow chart for checking the series conversion. Okay, any question? So the first thing you should check, if it doesn't satisfy test of divergence, then surely diverge already. If satisfied, maybe can converge. So if maybe can converge, straight away check whether it is absolutely convergent or not. Because if it is absolutely convergent, then the series sure converge. Okay, so you want to check some series converging, you can use all these kind of tests. Okay, if still doesn't converge, okay, is it an alternating series? If it is, try alternating tests. Everything try or cannot use already, then you need to use the original way. Look at the sequence of n partial sum. You ask yourself whether this sequence converge or not. Yeah. If all the tests already used cannot do anything or cannot show anything, then you need to go to the original way, very primitive way. Look at the sequence of n partial sum. Okay. Any question? Or question or no? Or question? Yes. Yeah. First, last result. Of course, we having saying that partial sum is the last resort. If you can't see the series, right? Of course, maybe it is helpful to write down a few terms like what we did just now. It's helpful to write down a few terms, but you cannot just look at that sequence. Otherwise, you will how to say? Maybe it will be kind of wasting time because we already have these tests in hand now, so you can use them first. Okay, if that's the last resort, then you need to look closely into the partial sum. Otherwise, you should try these tests first. 懂什么意思吗？如果有刀可以切，先用刀切先。刀切不断了，再去找其他东西来切，OK 吗？Yeah，不然的话你就浪费了这把刀。好，看到？Does it make sense? Okay. Okay. Right. So the last bit remember about this chapter is about rearrangement of a series. So if you have a series, okay, you can rearrange the term inside your series and then add them out again. Okay, so the problem, not the problem, the nice thing about this rearrangement is if you have a absolutely convergent series, okay, then every rearrangement of your series should be converging absolutely to the same sum. Okay, this is what we mentioned last time. So I want to quickly go through it, but I think we won't discuss deep about these two, not even the proof. So the proof, that means the proof is not very important. But to complete the theory, I want to put it into the notes. And for your level now, you should be able to understand the proof. Okay, you should be understand the proof, but the proof won't be tested. But I will put into the lecture notes for the completeness of the theory. So what's the rearrangement of a series? So if the two series contain the same terms. Same terms here, we can change order. For example, what? For example, the first series got 1 plus 2 plus 3. But the second series got 1 plus 3 plus 2. Or 1 plus... I cannot change already. I need to do 2 plus 1 plus 3. 2 plus 3 plus 1. This is what? This is something you learn in abstract algebra, right? You guys learn permutation, right? Permutation of numbers, right? Sn. So this bijection is the Sn. Okay, you can permute the thing inside here. But here got infinitely many terms, so you can do like S infinity. Okay, yeah. So you permute infinitely many terms here. Okay, so the first result last time we said is if your series absolutely convergent, so if your series absolutely converge, then any rearrangement also converge absolutely to the same sum. Okay, I put the proof inside this lecture note so you can read it, but it's not very important. But you should be able to understand the proof. So there's some trick they use. So that's why it makes this proof quite long. Yeah. I put inside the lecture notes, so please read. You don't need to add extra notes on this proof because we won't test it. Okay, we won't test it. But I want you to appreciate the proof. Okay, at least you should read it once. Okay? You should be able to understand what is it is written. Okay, but the construction is very long. And then the second statement is this Riemann theorem. Okay, Riemann theorem says that if the series is conditionally convergence, okay, and then it converges to something less than infinity, or even equals to infinity. Okay, I think I need to put down what is there. Okay, A is there. So if it converges, okay, if it conditionally converge, and then you have any real number, including infinity, I can arrange the sum to the number you like. Okay, so how you imagine this thing? So if it conditionally converge, what does it mean? Maybe there are positive or negative term inside there. So you group the positive term together, you group the negative term together. Okay, you group the positive term and negative term together. So your A, let's say, for example, your A is positive. Okay, so you can take your positive term add until the first place you exit A. And then you add in a negative term, add negative term until the first term you become less than A. And then you add positive term until the first term you exceed A again. And then you add negative term until the first term you becoming less than A. So you oscillate between this number. You can always do this because you are conditionally convergent. Okay, so you need to prove. Okay, why you can oscillate around A, and then you need to prove that when you do to infinite sum, it is actually equal to A. So there are two things you need to show here. Any A. See the proof. Okay, please see the proof. It's long because it's quite technical, but I think your level now should be able to read it. Okay, you should be able to read it. Okay, I will put this proof inside my lecture notes. The proof are not important for our exam purpose, but you should be able to understand now the proof. Okay, it's a bit long. Okay, a bit long. So I already tell you the construction. So what you need to do is you need to check why is it true. Okay, why the sum at the end come out to be equal A. I just tell you I can oscillate between A. And then why, okay, it is equal to A. And so you want to show something equals to A, right? So the technical part is you need to show, where is it? Yeah, you need to show it is very close to A. Okay, your sum is very close to A. So this is the technical part. You should be able to read it now, okay, and appreciate this proof. If you seriously can understand, that's fine also, because this proof is not important for the purposes of exam. Okay. Any question? Any question about this section here? So this section here is not too important because we are not going to use it in the next chapter at least. But for completeness, for the theorem, the theory, we will put it in. Okay. Okay. So if a series converges absolutely, then you can't change the sum. But if it converges conditionally, then you can change the sum. Any question before we end this chapter here? End the chapter of infinite series. We will finally go into the last bit of this course, which is the sequence of function. And then we will end the course there. The last milestone for your run. Any question before we leave this chapter? That series. Basically, it's a revision on what we did in calculus 2, and then we just fill in the proof. We put the proof back. Yeah. No. Okay. Okay. So for the rest of the how many weeks? 2 more weeks, huh? For the rest of the week, and then we will do a sequence of function, and then the place we end will be Taylor's polynomial. So also similar syllabus we did in calculus 2, also did Taylor polynomials. Actually, I will put that question into your assignment, right? You need to prove something, prove that you can get Taylor polynomials from the Cauchy mean value theorem. And then we will revisit it quickly again. Okay, if no question, let's take a break until 10:05. Then we'll come back for the last chapter.那你过程就是你觉得你教那个需要写出来给哦，所以可这个不是有那 example 还不用人出这个错，没有那个三边啊。那这里它是三吧？这部分它是三。Oh, it's on. I mean, yeah. I mean, 在theorem里面，这个是 BN set as BN，就是。好，那个，有一些人太笨了。没有，你要把这个写成theorem，把这个写成theorem。 看这个 BN 你知道是谁吗？他的8上 ，and then 这个是那哪里是毛的痛？它是孔的缺点，它不是毛的痛，因为它是这样也不是痛。所以你把这个减一和不 n 加一丢来这边，
啊，除掉，
对，
对吗？
这里丢掉，
这边其实
啊，
好像要存在耶，不然的话，
这边是
n 有 x 在里面，4号，
这样，
你这个你要说它是 convert 在一个点，还是
就是他那天
每一个点？
突然间说他重复，那就去
跟谁说？
应该是可以不是
因为你的 s 这个 s 是这个没有你要说什么点对不对？你这个你要说每一个点，说在那里点，它是可以取这边的这里，取所有的情况。
我只是想把这个
哦，
证明
这个是保的，但是问题是你要看的是爬学上面，这个一，对，后面呢
啊，
变成什么？double angle 啊？
上一跟上一个在其实 half 的再加再
大家这个
什么？再加sin a 加 b over cosine of a 减 b over。
去哪里找？
我这有买一个 summary 过去，跟他们去哪里一个
看的。
爱怎么好少的人，什么？
嗯，
但他今天我觉得基本上是挺简陋的。
没有啊，在哪里呢？
对，我这里听。
啊，你先给我，那个把你的有 cos 还是有 sin 呢？还是有 cos 还是有
可以
sin？
合完的，
都要合完。
和全部捆绑在一起，就全部有 sin 有 cos，它的包的它就可以包出味道密码。
对呀、但是我现在要包的是 partial sin 嘛。
那个它是不是 s x 不 sin x 加到去 sin n x 嘛，infinity x，
啊，对。
你会把它全部合在一起，变成 sin x 嘛 cos x 全部乘了。
呃，这样子的话，你要问 sin cos 加 sin 又是什么东西哦？你可以两个合嘛，对不对？哎，可是有时候如果是第三个那个话，像你 sin cos 加 sin cos 是什么？哦，sin cos 又变成两个 sin。
没有不是，因为那个 sin cos sin cos 啊，
然后
因为你是一跟二合在一起，然后三跟四合，
对对对对，
但是那个 cos 你都是一样的哦减 b，a 减 b 除 x 减二 x 除二嘛，
哦，可以啊，可以啊，可以
是三
啊，可以啊，可以啊。
三 x 除二，
所以意思说，even 的话都是可以啊，even 的话你可以 factorize 出来啊，也就是说，但是 factorize 过后，你还要处理，你要继续处理哦，继续处理剩下的 sin 哦，那边的 sin 就隔很大了咯，因为你是加了嘛，对，一个是1+2，一个是3+4，然后一个是5+6，这是3、7、11、
就感觉
17。那你要继续加哦，要继续研究，要继续弄，继续弄。
有点痛苦。
你这个我真的是不知道一起。这样哪里的说天生红是这个话，可能你
方式啊，
方正你这个号码 S 啊，所以你这个 S 我在问你，你到底要取一个真正的 F 出来，它就会方向对吧？就是我们现在要教的，
这个吗？做是方向对
你要做的 number one，就那个 S 你可以取简单一点，
换个然后
按一个太好算的话，这个不好算的一个算，就是我们接下来。你看这边没有 X 啊，它翻成号码，对吗？这个也很正常，关于没有 X 在里面的，它是放成出来的。
那个你在见自己，
是不是变了？就是绑出来。
哦，是有这个。
对啊，你这是 function，有 Dirichlet 它是 function， 但是你这样做，你直接去，或者你要 check，就是说 check 这一个conversion 在开那边就好，在一个点这个。
就不用放 interval。
你可以说这个 storage series 那个 conversion 再开，因为我们可以定到这个，这就不是。可以这样子，你可以 consider 这个，然后你check 它的 conversion 再开。
3%一个减去7%除2咯，
现在的。然后你下面算的时候，这边这个东西就下来除。然后你就是一个然后怎么算呢
？95次方。
哦
，90，
看一下
98跟95次方跟99。
应该你这个情况跟我们一样，是把这个解所以会到这个
99分之95，除99分之95
啊，那它不是两。
感受感受是吧？
你看，你要选你的点是好算的点，你看他选的点，选了过后，他这个东西只出一根针的，所以 sin 什么时候会出一根针？还有什么？
对，这个。
减到我2.0sin，让它会出这种版本。OK， 然后你把你的减1 over n 丢来这边也行。
这个
将你的第一个这个减1嘛，对的。
所以
减1和加1第一个
不可以等一啊。你们小过又拿定它们的等一啊。
1、2哦，对，1.1。啊，所以你拿到1张错，然后你拿到。
然后呢？减
3加1是，所以你跟他拿的一样，差不多一样。然后它是这个东西的下面，
减可以，
因为它
就是这个嘛，就是这个嘛，
可以。然后你把你的减1负的丢去然后你丢去另外一边，你还是有一个方法去的，对吧？是 OK。Alright, so finally we reach to the sequence of series. Sorry, what am I saying? Sequence of functions and also series of functions. Sequence of series 会不会很恐怖啊？觉得 topology 有给他们做的是 sequence of sequence， sequence of sequence， 你可以想象一下什么是 sequence of sequence。Yeah. Okay. So so what is sequence of functions? What have we learned before? Sequence of what we learned before? Sequence of real number. But now we replace real number by functions. Okay, we replace real number by function. So last time we used an, right, to denote our sequence. But now you can use fn because you have a sequence of function. f1, f2, f3, f4, f5, f6. So what is a sequence of function? So a sequence of function. So last time, how do we think of a sequence of number? We think of it as a function from where to where? How do we think about sequence of real number? We think of it as a function of what? Function of what? Natural number to real number. But now we replace real number by function more. So we can think of it also as a function from natural number to a set of what we consider here is a set of real value function. Okay, real value function with the same domain A. Okay, with the same domain A. Functions with a same domain A. So meaning I give you a natural number, you need to give me a function. Okay. So what function is this? This is a real value function. Okay, real value function. And then they have the same domain. They should have the same domain. And then we call it A. Okay. So you can think of it as a function going from natural number to a set of functions. So why I write like this? How do you read this statement here? This symbol here, r to the power a. What's this? This is a function, set of function that maps a to r. Function that maps a to r. Okay? Know how to read this? A function that maps a to r. Okay? So, meaning I give you a natural number n. Okay? You need to give me a function here. Call it fn. And then what is fn? Fn is a function from a to r. Okay, make sense? So you should think about the analogy. Sequence of function is what? I give you a natural number, you give me a r. But here, I give you a natural number, I give you a function. Okay, what does this function do? This function maps a to r. This is just a notation, r to the power a. Notation. This is a space of function, set of function. Okay, that maps a to r. Does it make sense? Make sense or not? Any question about notation here? Any question about notation? So sometimes we will write bracket fn, or we will write curly bracket fn. Okay, so similar to the an case. Okay, so maybe we'll specify where we started. Okay, where we start the n is the same. Yes. Small n. Where's the small n? And go to. So n small n 是 n 的 element. Okay. Yeah. Function of function. Yeah. A 是 domain of 那个 fn. 因为 when you want to specify function, right, you need to have domain, right? This one is the domain for fn. Does it make sense? You see a function as an element, 一个东西. You take one natural number, get one function. But to specify function, what do you need to specify? You need to have a domain to start with, right? Otherwise, what's function? Yeah, no. So the here is that we go up a level. Okay, function of function. Okay, function that give what? That give the image, which is a function. This is the image. So let me write down here. So you can imagine that f1 is little f1, f2 is little f2. Okay, but f1 is a map from A to R. And then F2 is also a map from A to R. So it's not number anymore. Your image is function. Okay? Your image is function. 什么？不一定哦，不一定嘛，对不对？我就像普通的sequence 罢了，sequence 也可以是 constant sequence 啊，对不对？我现在也可以是 function 都一样，不是叫 constant function 啊 ，constant function 有另外一个意思，对不对？我会 talk about constant function. Constant function says you send everything to the same thing, but the function are the same. Okay. Okay or not? Any question? Any more question about this definition? It's quite important. I want you to appreciate this definition because we can keep defining function or function or function or function or function or function. So this is like you can do it inductive. Okay. Yeah. Now the first level you get is function or function. Okay. No, no. Okay. Okay. So we will use this idea to think about sequence of function. So later I will let you see very concrete example. Don't worry. So now we will define a new convergence. So suppose Fn is a sequence of function. Sequence of function defined on A. Okay. So for now, what we take the domain for is a subset of R. Then we will say that the sequence Fn of functions converges pointwise. It converges pointwise. Function F. If, again, if for each x naught in A, limit of k of fk Sn equals to fs naught is equal to fs naught. Okay. So in this case here, we will write converge to f pointwise. Okay. So if you study the this limit here, what is changing? What is changing? What is changing? K, right? Okay, K is changing, but S naught is already fixed. So ask you a question. If you have a function F1 X naught should be a number. So what you are looking for here is a sequence of number only, because I fixed X naught already. Okay, so actually I check every point in A, and then I see how the function value change. Okay, so this is called the convergence pointwise, because we already fixed the point. We only check at each point. Okay, we only check at each point. So that's why we call pointwise. Okay, so that's why we call pointwise. We check at a particular point. Okay, so sequence of function become checking the limit of sequence function. Pointwise become checking a limit of sequence of number. Okay. Yeah, good, very good. Good observation. So let me see what's the example we want to look at now. Right, good. Okay, so let's look at one example. We need to be very careful because this is a very new thing to all of us. So consider for each k n, okay, we will consider this function here. Okay, you can say, oh, what the heck is this guy? Okay, s to the power 2 plus 2k plus kx over k. What's this function? What's this sequence looks like? How does this sequence looks like? You can try what is f1. What is f1? S squared plus x. F2, eh? Two x over 2. F cube, eh? 3x over 3, and then so on. Can you imagine this picture or not? Can you imagine this picture here? Huh? What's that called? Is it hyperbola? Hyperbola? Parabola? Okay, parabola. Oh, hyperbolic. Okay, sure, good. Parabola. Okay, parabola. But how do you draw the parabola? Parabola, you need to find the roots, right? Okay, so what's the roots here? Like for the first one, where's the roots? 0 and minus 2. I don't know, because you can write it as, sorry, not minus 2, minus 1. Right, you can factorize it into x times x plus 1. I don't know. Okay, second one, x over 2 times x plus 2. Then the third one, x over 3 over x plus 3. So in general, you can find the roots. Correct or not? In general, you can find the roots. What's the general roots here? X over k times x plus k. Okay. So what can you see here? First root is always what? What is the first root? First root is always 0. Okay. First root is always 0. Then for the next root, it decreases. Decreases. Okay. So the first parabola you have is having roots -1 and 0. Second one, you should have -2 and 0, -3 and 0, -4 and 0, and then keep going. Okay, keep going. So I suggest you a very good X to use, GeoGebra. Can go and try on GeoGebra. What time is it? Okay, I give you 4 minutes. You have tablet, right? Go GeoGebra. Plot the sequence of C function. This function here. Okay, I plot, you also plot. Then later we'll share diagram. Go GeoGebra. GeoGebra can plot a function. Go GeoGebra, graphing calculator. Okay, try and type a few of them out. F1, F2, F3, F4, F5. Okay, try and plot it. Give you 4 minutes. We all plot together.很热是不是？我觉得冷气坏掉哎，它出热气，它叫热气。 if you find very hard to maneuver around this variable, you can use this arrow left right here. It's easier. You can use this left right. Okay, how many F you have plotted already? How many F you plotted? 3, 9. Okay, good. Okay, let's look at our graph together, your graph and my graph. Okay, so I have plotted 1, 2, 3, 4, 5, 6, and then I go to 50 and 100. Okay, so if you want to look at convergence points wise, what did we say just now? We need to fix a point. Okay, let's say we fix this -4, can or not? Okay, let's fix -4 for x0. What is f1? F1 is pretty high. Okay, maybe we fix a lower one. Let's fix -3. Okay, let's fix -3. Okay, what is F1? My F1 is F. Where is my F? My F is the green one. Okay, let's look at this point here. When the F increases, what happened with F and -3? Here. Okay, maybe I use mine already ready-made one. Okay, use my ready-made one. What do you mean? Oh, hey, you are brilliant, are you? You are technology kid. Let's look at x equals to -3. Good, yeah, good. Okay, so if you look at this line, what happened to this value of f? The value of f seems decreases, correct or not? You see, f1 is so at 6, f2 is below 2, and then f3 is 0 already because it's become one of the root already, right? When x equals to -3, and then you can see that it keeps decreasing, decreasing until this line, almost reaching this line here. Later, I'll tell you what's the significance of this line. And how about 0 have nothing to check because for every n, fn0 is just 0 because 0 is one of the root. How about the positive part? Let us check another line. What line to check? Can I add another one? So we can duplicate. So let's check y equals to 4, x equals to 4. X equals to 4. Okay, so what happened as s equals to 4? You also can see that from the first f1, it decrease until this line here. This line has a significant effect here. If you zoom in much, you can see that this line is almost equals to y equals to x. Although if you zoom out, it's still parabola. But if you go further enough in the sequence, you can see the effect of y equals to -x. If I zoom in enough, see? Is it y equals to -x? Not quite, is it? If not quite, then I try to add one more. Go further a bit. Go to 1000. F1000. You can see that F1000 almost slashed the graph into half at y equals to x. Can you see it? Can see or not? Can see or not? Okay, but if you zoom out again, still parabola. It's a magic here. Okay, so how do we show this magic analytically? So we are mathematician, right? So we want to see this effect here. So what do I mean? So let us compute analytically for all S naught in R. If we're gonna compute the limit of FKS naught, what is it? What's our formula for FKS naught? S naught square plus KS naught over K. So this is a number, correct or not? So how do we compute the limit of this guy? Yeah. Okay, sorry. Let me remove this. So we're gonna show this analytically. So what happened if we take for all points? What is FKS naught? It is S naught square plus K S naught over K. But what's the limit of this guy? This is the sum of two convergent sequence. Okay, sum of two convergent sequence. So what do we get in the end is just S naught. Okay, so in this case here, what do we say here? Since S naught is arbitrary, limit of K to infinity of Fx is just X. Okay? This means that Fk converge to the function Fx equals to X point-wise. Does it make sense? Okay. For every point, it will converge to for every point, Fx will converge to X. Okay. And then how you appreciate this? This is what I show you in the picture just now. Okay. So for every X, you will converge to this line here. This Y equals to X line here. Every point you will converge to Y equals to X line here. Does it make sense? 可以明白吗？可以明白吗？可以综合两个东西一起来看吗？一个图像，一个是 limit， 综合起来看 ，OK 吗 ？OK 吗？有问题吗 ？Any question? Very important question. A very important example here to appreciate what is point-wise convergence. OK or not? 有问题吗？有问题吗 ？Yeah. Please ask if you got question here. OK， 虽然呢，你一直 zoom out， 还是一个 parabola， 但是就在那个点上面的时候，那附近就像一个 y 等于 x 嘛，很重要的一个 concept 嘛。对，虽然整体来看哦 parabola， 但是你放近看，它就是一条，它 convert to 一条直线，算直线吗 ？y equals to x。OK， OK 啊，很重要啊 ，very important 啊。Okay, so you can use geometry to help you to see the answer, but you should also need to prove it analytically. Okay, you should be able to prove it analytically. Okay. 图片可以帮你找 intuition， 但是你要能够 show 啊。OK， 用 limit 或者 epsilon delta 等等。Make sense？ 可以理解吗？可以理解，我们就 go to next example。让你猜一下这个 point-wise conversion 的 function 是谁 ？OK， I think about here, I think we should stop already. OK， so 给你另外一个 example， 你可以让你去玩 GeoGebra 也可以，但是我要你猜一下， so 猜一下这个 function， so for 0到1 x， so x live in 0 to 1 and your fnx is x to the power n. Okay, so let you guess, what's this f have to converse point-wise to? 你可以拿你的那个 GeoGebra try 一下，然后跟你朋友讨论一下。OK， converse to 什么 f point-wise？ 可以拿你的 GeoGebra 给你们10分钟讨论，画一下。 差一点点，差一点点。画一下图，差一点点。almost 等于0啊，那个方程。almost 等于0。猜一下，它 point wise convert to 什么 f？ 你可以 check 一下 f1 是什么 ，f2 f4，看它 convert to 什么方程。point wise 啊，this one is just point wise 啊，我 only check for every point。point wise， 正方形。找到了。Anyone found something interesting? You can screenshot and share to me in the team chat, and then I can share to everyone. Anyone found something interesting in the GeoGebra or not? You can screenshot and send me, and then we can share again to everyone. Whoa, what did NgeKieSeng found here? Why NgeKieSeng, your color is black and white only? Oh, wow, this is you guys really a tech guy, tech kid. Okay, so if you use Desmos, Desmos can put can set your n. Wait, this one like a mass knot. You can set your n to be all the value you want, but it's black lah. Maybe next time they can put different color. But where should we focus on? Our function only take values from 0 to 1. So you can focus on this grid here. Correct? Okay, we can focus on this grid. So you see so many lines. Where's the sequence? From up to down or to down to up or jump here, jump there? Should be up to down, right? Because the first sequence is what? Y equals to x. Second, y equals to x squared. And then s cubed, x to the power 4, s to the power 5, s to the power 6. So that's why you can see you got parabola, and then you got this, how do we call this? I call this snake. Snake, is it? Looks like snake. When do you get the snake function? Oh, yes, good. The odd power, s cubed, x to the power 5, x to the power 7. Okay, but we only focus on here. So what can you observe here? If you look at the cross section of one line, right, you can see that the value of fx keep decreasing. Decrease until where? Until 0, you see? When you get very large, wow, 20, 100, 1000, 10,000, we really 10,000. You get the 10,000 one. You see, the 10,000 one is pretty close to 0 function. But you see, when it is really close to 0 function, what happened? It still go up. Still go up. Still go up until that when it is x equals to 1, your function is always 1. Correct or not? Correct or not? No matter what power you take, 1 to the n is always 1. Okay. Okay. So what's the f you guess here? What's the f? You want to guess what's the f from this observation? Good, very good. So fx should be fx should be equals to fx should be equals to okay, equals to 0 if your x is in 0 to 1, and then 1 if s equals to 1. So the problem is how to show this. how to show this pointwise? How to show it? So you need to check that for every x in 0 to 1, what's the limit of this function? The value of this function. This is limit of x to the power n. But this x is always less than 1. For example, 0.1. What is 0.1 squared? 0.01. What is 0.01 to power 4? For example, 0.0001. So if you take power on number less than 1, what is the limit? It is 0. Okay, you're getting smaller and smaller number. But for x equal to 1, what is this limit here? What is fn1? fn1 is always 1. Because 1 to the power n, right? So it's always 1. So limit of 1 is what? 1. Okay. Limit of 1 is 1. Okay. So we can see that, this x to the power n converges pointwise to this piecewise function here. Did you observe anything here or not? Did you observe anything? We have learned so many things about continuity, differentiability. Did you observe anything here? What property does this Sn take? Continuous. But Fn? Not continuous. So you could have a sequence of continuous function that converges pointwise to a non-continuous function. Does that make sense? So meaning what? Continuity is not preserved by this convergence. It's not preserved. Like convergence of real number, right? Can you converge to something not real number or not? Cannot, right? Okay, but this is the property of real number. But in this case here, convergence, pointwise convergence of a continuity function might not be continuous. It might not be continuous. Question? Go question. So pointwise conversion doesn't preserve continuity. Okay. Doesn't preserve continuity. So next week, we're gonna learn uniform convergence, and then that convergence will preserve continuity. Okay. So the limit of uniform convergence function should be continuous. Uniform convergence of sequence of continuous function should be continuous. Okay. We will introduce it next time. Okay. Uniform convergence. Yeah. I think a bit more, or just that. Okay, maybe we left to next week. So we will introduce new thing about uniform convergence. Okay. But I want you to get today is pointwise convergence don't preserve continuity. So you have continuous function that pointwise converge to something split away, so not continuous. Okay. Does it make sense? Okay. Okay, any question before we break? Any question before we break? Any question before we break? No? Okay, so next up we will introduce uniform continuity. Yeah. The